Welcome again to another edition of second semester OChem. In today's look, what we're going to do is evaluate our nucleophilic addition and elimination reactions with really our first full-blown nucleophile, our hydride nucleophiles. We already saw these pop up in the previous unit when we looked at sodium borohydride and lithium aluminum hydride. Both of those are ultimately doing the same thing. They are supplying an active H-. And as hopefully you remember from the previous unit, if we go through and look at how those structures break down, we'd see a Lewis structure with a negative charge on the aluminum. But hydrogen being more electronegative than aluminum, that electron density and ultimately its reactivity is better kind of considered with a hydride or a electrons on the hydrogen giving us hydride. And that's ultimately the activity behind these. So you could really just kind of cheat and just as soon as you see those reagents, immediately go to H-. One of the things that you do need to remember about this particular H- for those is that this one is not particularly, well, actually, no, I'm not going to say that. There are other H- that are not nucleophilic. For instance, sodium hydride is only basic. Okay, it can't act as a nucleophile. Lithium aluminum hydride and sodium borohydride do have a high propensity to act as nucleophiles, and that's due largely to the aluminum or boron stabilizing that central structure. So if we remember the hydride attacks, we break that pi bond, and our oxygen picks up its electrons from somewhere in the environment. If we were to go through and look at our example for our nucleophilic addition elimination reactions, we're going to see a very similar mechanism run through this. We're taking our H-, which can then come in, attack, and break the pi bond. As is characteristic for all of our nucleophilic addition elimination reactions, we should be showing, on particular mechanisms, we should be showing the formation of that tetrahedral intermediate. It's the tetrahedral intermediate because, well, we have a tetrahedral carbon. That carbon is sp3 hybridized and is tetrahedral. In the previous unit, what would then happen is that we would have a solvent molecule, usually methanol in the case of borohydride, react and give us the alcohol. While that is a potential outcome, the issue with that is that if we looked at the result, we would end up with two very electronegative elements connected to that tetrahedral carbon. Okay, so that carbon is now getting a lot of electron density being pulled away from it, and it ultimately isn't really a fan of that. Okay, that mimics our hydrate or even our acetal type formations. And as we saw, those formations weren't stable and very readily shifted across or back to the keto or carbonyl form. So what does that mean? That means we aren't going to pick up a hydrogen, at least not yet, from our solvent. What we will do is acknowledge that the carbon wants some electron density. It'll steal them from the oxygen, thereby kicking out the chloride. Because that chloride is a decent leaving group, this works out for us. And what we would end up seeing would be the reformation of that pi bond, and we would now have our aldehyde, and we'd have chloride floating around in solution. Okay, and this is where people will, or books I've seen in the past, will push this as now it's a new reaction and now new things happen. Well, nothing really new has happened. The hydride came in and attacked. Why is this functional group potentially different? Well, if we evaluate this, this is an aldehyde, and we know that the aldehyde in the presence of sodium borohydride reacts. So we end up getting a second hydride nucleophilic addition. That second addition gets us now to that oxygen with the negative charge that can't really stabilize. Now it can go out to the solvent, and we can pick that up from our solvent. okay? And we would end with our final alcohol. So what you're trying to do is acknowledge that all you're doing is stacking chemistry. You're taking the chemistry that we already learned with the nucleophilic addition, and you're also acknowledging that the nucleophilic addition elimination reactions give you the substrate that allows for the continuation of the reaction. It's not a new reaction, it's just a repeat of an old one. Okay? But you have to have the foresight to see those patterns build into it. Otherwise, what you end up doing is just saying, oh, I'm going to memorize that it reacts twice. It's up to you. Okay? So then it would stack out. We get our alcohol all nice and dandy. But remember, we said we had sodium borohydride and lithium aluminum hydride, which had varying reactivities. And if you remember, we also said the same thing about our acid derivatives. The acid derivatives had varying activities, which we approximated by saying varying abilities of that leaving group. So we now have two different reagents with two different kind of sliding scales on reactivity, which then means you have to know to associate which reagent with which to allow for that reduction. Okay, so if we go through and look at these, our sodium borohydride versus our lithium aluminum hydride, really what I want you to do is key in on the big differences. Instead of looking at everything that's the same, let's note the difference. The difference comes in right here. If we look, we're looking at a carboxylic acid and an amide. Those don't react under sodium borohydride. They do react under lithium aluminum hydride. Why might they react under lithium aluminum hydride? Well, as we learned, lithium aluminum hydride is a more active reducing agent. Okay? And that's why it's going to continue to reduce, even for those less active species. But if we have a very active electrophile, I can use either one. It doesn't really matter to me. Okay, so why would I choose one over the other? Well, a lot of that's going to be your secondary structures. Okay, so for instance, if your acid chloride, which it wouldn't, but let's just say it did, had an alcohol somewhere in that chain, sodium borohydride is probably going to be a better bet because the lithium aluminum hydride is going to react with the alcohol and you'll get secondary reactions. Okay, so what we're trying to do is recognize those patterns and decide when should I use one versus the other. Okay, again, because we're in the nucleophilic addition elimination chapter, okay, we tend to ignore or forget that we already addressed these reactions. Okay, and that's what's kind of hidden in gray there. If you look really carefully, what those are your aldehyde and your ketone. Those get produced in a lot of these reactions. And if they get produced, the reaction continues. Okay, so we just have to be kind of cognizant of that. We are moving down the ladder typically as we move through these. A lot of it's going to do with the reactivity. Hydride as a nucleophile, stupid strong, okay, which means it's going to continue to react. Okay, and it might even allow you to move up the ladder depending on that reactivity. Okay, so let's take a look at those two that didn't react, so our kind of oddities. So why would we expect the esters, okay, and it says barely. If you note here, I would argue it's a bit misleading. They have this kind of grayed out. This reduction is very, very slow. Really what they're saying is that if you want to reduce an ester, don't use sodium borohydride because it doesn't work very well. Okay? But that still takes us to the point of why would esters react, but not the carboxylic or the amides. Okay? Well, what is the difference between all of those functional groups? And ultimately what it's going to do is how is that atom changing the reactivity? So if we were to compare, as we've got listed out here, because we know the ketone, the aldehyde, the acyl chloride all react, we can say, well, they're all high up on the list, right? They're all higher up, and therefore with sodium borohydride being weaker, there's going to be a line that prevents it from reacting. Okay, well, why is that line there? What is so special about the ester that makes it less active? Okay, then say, we'll go with the ketone because it's the closest to it, right? Well, if we go through and evaluate, we'll typically get students saying, well, that is more positive than that carbonyl. Okay? And the reason you might say that would be inductive. That oxygen is withdrawing more electrons, right? And it thereby makes that carbon more electrophilic. But if that was the case, shouldn't the ester be more active than the ketone and aldehyde? So there's got to be something wrong with your analysis. Right? And to that, I would say, well, did you actually use those rules that I told you to use for reactivity? Charge, size, electronegativity, resonance, and induction. Well, there's induction. It's there. It's the fifth on the list, though. It's the last thing you should look at. Okay? The charge, the size, and electronegativity, all those atomic effects for that carbon, identical. So we'll ignore those. We'll look at resonance. Is there resonance in the case of the ester? Well, yes, there is. What does that do to the stability? Okay, and this is where people go, well, that's a horrible resonance structure. That's actually not relevant. This resonance structure exists, okay, so we need to consider it. What does it do to the stability of that carbon? It makes it more stable. Well, if it is now more stable, that makes it less electrophilic. That's why it's lower on the ladder. Okay? So we can use charge, size, electronegativity, resonance, and induction to help us predict this and see this. Okay? We can further use this to our benefit, as this reaction up at the top is kind of suggesting, I guess right there, as the reaction is suggesting, because sodium borohydride only reacts in some cases but not the others. So if we looked at a structure as shown that has both a ketone highlighted, and an ester, I can go through and reduce one of those to an alcohol, but not the other, if I use a proper reagent. That proper reagent must be selective for one over the other. Okay? In this case, the sodium borohydride will react with ketones, but it won't react with the ester. So if I pick sodium borohydride, I get the reduction the way I want it to. If I picked lithium aluminum hydride, both positions get reduced. So this goes back to what we talked about in chapter 19, I think, with selectivity of our reagents. Sodium borohydride and lithium aluminum hydride are selective. That selectivity really comes into play in this particular unit. We didn't see it as much in the last unit because ketones and aldehydes both reacted. But here we do have that difference. Our acids and our amides don't react with the sodium borohydride, but lithium aluminum hydride will. That's a big difference. We need to be watching for that when we go through and pick reagents for our syntheses and also for multiple choice questions. Okay. Why would lithium aluminum hydride actually react? Well, as we talked about in the last unit, it's more active. But why? Lithium has a stronger connection with the oxygen of our carbonyl. That stronger connection polarizes that bond, making the electrophilic site much more active as an electrophile. What else? The aluminum is larger, which changes the distance between the hydrogen and that metal center, making that hydrogen more active because it's further away from a neutralizing species, that aluminum, or in the other case, the boron being a smaller bond. So if we look at those atomic effects, it explains their reactivity difference. Okay? We could go to experiment and just memorize, or we could try and evaluate and use these pieces that we've talked about for, what are we looking at now, 20 weeks? Okay, so lithium aluminum hydride would take it all the way out, get our full reduction. Okay, so I like to throw this one in here because I didn't really push this too much. So hopefully you didn't actually see it on the last slide on what happened. If we talk through our reactions, we've got that carbonyl, we've got a polar pi bond, we should go through, have the hydride react. This is an amide, should be standard, and we should reduce the amide. Reduce it to what? Okay. And if we spent that time to just memorize things out, I would bet with a fairly high frequency, we're going to get people telling me we get an alcohol. Okay? And maybe you get this other piece chilling out here too. And we could put the hydrogen on there. Okay? Because you go, well, carbonyl, it reduces to an alcohol. No. Okay? Polar pi bond reduces. Okay? What we have to watch out for is what's the chemistry that's happening at each of those stages. So let's walk through this process. Let's start with what we first had, that hydride. Hydride comes in, attacks, breaks the pi bond. Nothing different about that. That's still all the same. There's our negative oxygen, lone pairs. There's our nitrogen with all that junk, and our hydrogen. And now we run into kind of a dilemma behind this. Which atom wants the electrons more? Okay? Because we could very well see something like this going on, okay? Which would then kick out that nitrogen, and that would suggest that you're right. Okay? But remember, we're in a very, very basic environment, so that negative oxygen isn't horrible. If we add to the fact that that lithium is floating around, and to that fact that we now have an aluminum floating around, okay, with that empty p orbital that could coordinate, that oxygen is really not all that negative. And so why bring this up? Well, when we look at it, we're saying, well, the oxygen's the source of electrons. Well, is there another source of electrons? The nitrogen, okay? In all our past cases, if you go through and look at it, the acid chloride, the ester, all of those are oxygens or atoms that don't form more than one bond. Nitrogen's a bit of an interesting character because nitrogen can form more than one bond. So nitrogen does have those electrons. Well, which atom would be better suited to share the electrons, the nitrogen or the oxygen? Wonder if there was a way we could evaluate that without having to memorize something. Oh, charge, size, electronegativity, and resonance. We just went through and looked at charge. The charge is effectively neutralized. We looked to size, oxygen and nitrogen, same row on the periodic table, no real difference. The next one's electronegativity. Well, oxygen is more electronegative. Well, if it's more electronegative, is it going to be more willing to share electrons or less? Well, more electronegative means it's holding the electrons. Well, dang, that means nitrogen's more willing to share the electrons. What does this mean for us? Okay, well, this means that oxygen ends up getting ejected. And yes, if you're thinking about this and going like, but isn't that an O-2? Well, as I said, this is what our aluminum and our lithium are doing for us. They're really stabilizing that oxygen and allowing it to leave. You're forming an aluminum oxide. That aluminum oxide is surprisingly stable, and it facilitates this reaction. What does that mean for us? Well, then that means I don't have the oxygen connected to the structure anymore. And this is where nitrogen's chemistry kind of gets in the way and goes, well, it can do different things. This would now be positively charged. Nitrogen doesn't want to be positive, so what happens? Another equivalent of the hydride comes in, breaks that. We'd have our two hydrogens connected. We'd have our nitrogen with the lone pair. And we would end with an amine. Okay? That amines substitution is going to depend on what these groups are. Okay? If those are hydrogens, then we'd be looking at a primary amine. If we were carbons, then we're potentially where we are now, a quaternary amine. But what we have to acknowledge is this key kind of clutch state in between in the mechanism is what's allowing us to differentiate those paths. It's oxygen versus nitrogen and their abilities to share the electrons. That ability is something that we've already established when we look at electronegativity. If we move to the next step, people go, oh, but I never saw that kind of reaction. Well, you have. That's a polar pi bond. That's a difference in electronegativity. That's a double bond. That's a pi bond formed by p electrons. Those are all things that you learned in first semester. And all you're trying to do is apply that content from first semester to now. If you don't apply that content, then what you are doing, which is okay, what you are doing is going back, come on, to this, and you're memorizing this, all of this. Okay? That's okay. Just realize that's the boat you're jumping into. Okay? And when something goes slightly weird, you're now stuck because you can't apply it. I'm pushing the application so that you can apply it and you can see this when you move into biochemistry, okay? Or when you move into your pharm classes. Okay? That's what you're trying to do. Okay? That's the point of taking the class. Okay? So after that, we could move to these two situations. We're starting with the acid chloride, very high reactivity. Why does my eyes keep looking down? I thought I was looking at the camera. Irritating. Acid chloride, so very high on the list, going to an aldehyde. Well, the aldehyde's also very high on the list. Shouldn't that continue to react to an alcohol? Okay. If we look, ester, fairly high on the list, or that's a lie, it's at the bottom of the list. But if we reduced that, we would get to the aldehyde, which is actually higher on the list. So wouldn't that go down to the alcohol? And based off the chemistries we've addressed with our lithium aluminum hydride and our sodium borohydride, yes, absolutely, they move all the way through. Okay? But just like we learned with our oxidation reagents, say with chromic acid versus PCC, we can create reagents that don't go all the way. There's something limiting them. In the case of the chromic acid versus the PCC, it was a structural thing. Pyridine structurally couldn't allow for that hydrate hemiacetal formation so that you didn't get a second oxidation. Okay, so could we do something similar with our hydrides? Instead of doing sodium borohydride, could I remove one of those hydrogens and put something else on there that could potentially sterically limit the reactivity? Turns out yes. Okay, and so what we encounter are two common reagents that pop up. DIBAl is probably the most common of these two, just for your reference. So if you were going to go through and memorize something, DIBAl is a good one to memorize. And I botched the, oh man, I'm just going to make it all capital. Apparently not. DIBAl, diisobutyl aluminum hydride. Okay, it's still an aluminum hydride, but now what we've got out here are isobutyl groups. Okay, for those of you paying attention, those are sterically massive. Okay, however, it still has that clutch aluminum hydride reactivity. That hydride is still more electronegative than the aluminum. It is still negative. So we still have that reducing hydride. If we move up to the top case is a little bit better because we aren't using an acronym or I think that's right. We're actually showing the structure sort of. Okay, and by sort of, they're kind of fudging with it a little bit, but there's our aluminum, and then we have 3 tert butyl groups. And again, for those of you paying attention, that is a lot of sterics. Okay? Those sterics are going to limit that reactivity and ultimately prevent it from reacting quite as much. Okay? And that's really the point of these reagents, is these reagents modify our aluminum hydride so that they react very specifically with these species. So in this case, that top one is acyl chlorides to aldehydes, very specifically. The bottom one, that's talking about esters going to aldehydes, very specifically. Right? And so what you should be aware of is note that the chemistry is still there. It's still a hydride, but we added something to it to mute okay, or change that chemistry. And for those people saying, but if I saw this on exam, there was no way I'd ever know how to pick this up, what you should be memorizing is that sodium borohydride, lithium aluminum hydride. You can modify those hydrides so it changes the chemistry. So if you see a modification, don't go all the way, because there's really two stages. Okay? So if there's a modification, stop. Do it once, done. That's it. Okay? That modification is there to limit the chemistry. Okay? You go, well, why would you do that? Well, if it didn't limit the chemistry, why the hell did you use that reagent? Why not just use lithium aluminum hydride or sodium borohydride? Right? That's the point of being able to recognize those patterns so that you can adjust your expectations moving forward. Okay? The last thing I want to draw your attention to on this before we look at the summary for it, these are frigid reactions. Minus 75, minus 78, you're looking at very, very cold conditions. Those cold conditions will also limit reactivity. Right? So we've got sterics pushing for us, and we have that cold reaction pushing for us. Okay? So again, DIBAl, common acronym, that shows up all over the place. I would recommend that you memorize that one. The other one, I don't have a common acronym for. Okay? Both of them, what you're looking for is that aluminum H bond. That's it. Okay? And that's really what you should be picking out of this. Okay? Is not going, oh my God, more reagents. Metal hydride. That's it. If you see the metal hydride, you have a hydride nucleophile. React it with an electrophile. That's the point. This is why I've pushed understanding those key characteristics of chemistry: electrophile, nucleophile, acid, base. Right? The reactions: acid, base, substitution, elimination, addition, and radical. And then the qualifiers that can move after them: charge, size, electronegativity, resonance, and induction. Okay? That's the point of that, is so that you can apply and get this without having to memorize a whole bunch of nuanced stuff. Because I don't know about you, trying to memorize LiAlH parentheses OT parentheses 3, slim to none that I'm actually going to pick that up. Okay? Just my 2 cents. Okay? So hopefully with that, you've got something, you can move forward, you can work with this, and good luck. Wrong stop. Where's my mouse? There we go.